There we go. Okay. So the chain rule is, it encompasses all of the other rules inside of itself. So this one's kind of the broadest one. Let's say we look at number 5 down here. So let me try to leave that rule up. So we have a sum and difference of things. So first of all, we need to recognize that, remember, whenever you have a sum or a difference of functions, you just take their derivatives separately. So we kind of need to separate this into its 3 pieces. So we'll take the 3 derivatives separately. That first derivative, the 5 natural log of 2t squared plus 2, is a chain rule. So that 5, remember, whenever you have a constant times a function, the constant stays along for the ride. One of my screens is lagging a lot, the other one not too bad. Hello, screen, you can do it. I believe in you. There you go. So that 5 comes along for the ride, and then we need to take the derivative of the natural log of that 2t squared plus 2. So that's a chain rule. Since we have an outside function of the natural log, we have to take care of that first. So the natural log of essentially anything is 1 over that thing. So we have 1 over 2t squared plus 2. But then we have to take the derivative of that inside function of the 2t squared plus 2. So the derivative of 2t squared will be 4t. The 2 that is in the front stays. When we bring down the 2 from the power, 2 times 2 gives us 4. And then plus 0, the derivative of 2. So I'm just going to erase that now and just write 4t. So we've taken the derivative of essentially that entire first piece. So we're done that. Now we have to take the derivative of the 7t squared. 7 comes along for the ride. You bring the power down, so you'll get 14t. And then subtract the derivative of 9. Since there's no variable attached to that, it's just a constant. Derivative of a constant is 0. So of course you don't have to write it if you don't want to. The only way you could possibly simplify that a little bit is, see how in that first term you have a 5 in the front and then a 4t in the back. You can multiply those two together to get 20t. And you can also put it on top of the fraction, but that's, again, not really necessary. I don't require you to simplify these at all. Simplify it to 20t over 2t squared plus 2 plus 14t. So as always with these derivative ones, I'm kind of going to pause slightly afterwards in case anyone has questions. Please catch me. Otherwise, just keep chugging. I see a hand. Oh yeah, David, what up?
Okay. Even though we mentioned like don't simplify, is there a point where we're gonna have to get to that soon, or just that one thing?
So we'll want to simplify a little bit. So like simplifying this much will be nice for chapter 4. It's not necessarily even required for chapter 4 per se, but it'll definitely make the algebra a bit nicer. We won't have to do like anything super crazy to simplify it, but just kind of simplifying some constants and grouping them together is going to be helpful for chapter 4. So.
Okay, no problem. Yeah, it just got me curious, but either way, that works.
Mm-hmm. So if it's just these generic find the derivative questions, you don't need to worry about it. But the stuff we look at in chapter 4 might be helpful. All right, so let's look at this last one in the chain rule section. Let me get back to the regular chat. There we go. So again, we have a difference of things. So we essentially have 2 different pieces that we need to take the derivative of. Each one is going to be a chain rule in this case. So the first one, we have 2e to the x squared plus 7. So that 2 in the front kind of comes along for the ride. And then we have e to the x squared plus 7. So we're essentially in an, let me scroll down a little bit. So remember, I kind of gave us this tip at the bottom that you kind of have those 3 options of what kind of situation you're in. We're in an e to the z situation. So our derivative there is you essentially just rewrite the entire e to the something. But then you have to take the derivative of that something of the x squared plus 7. One screen's lagging and the one's not. Why is it doing that? Let me try this. Blank. There we go. So we have to multiply by the derivative of x squared plus 7, which will give us 2x plus 0. So I'm not going to write it. because the derivative of 7 is 0. If you like to write those, you feel free to do so. So then we're done taking the derivative of the e thing. And so we now have to subtract the derivative of that 5 natural log of 2x minus 1. So the 5 comes along for the ride. Derivative of the natural log of essentially anything is 1 over that thing. So we have 1 over 2x minus 1. But then we have to take the derivative of that 2x minus 1. So derivative of 2x will give us 2. Derivative of 1 will be 0, so I'm just not going to write it. In general, that's a perfectly fine stopping point, but if we wanted to simplify it a little bit, we could kind of lump those constants together, the 2 and the 2x in the first piece, and then I'm going to multiply the 5 and the 2 to get 10. And I'm also going to put it on top of the fraction bar. One thing I'll say for chain rule is that chain rule is used an obnoxious amount of the time, and that's because chain rule comes into play. So originally we looked at rules for e to the x, natural log of x, x to the n. You know, we kind of had these, you know, basic rules at the beginning. If that thing where that x is something more difficult than just an x, and by that I even mean a 2x, an x squared, an x plus 1, if it is anything more than just a simple x, it's going to be a chain rule. And I got rid of my chat, so where did I get the 2x? Yeah. So that 2x, I assume you mean this guy. So we were taking the derivative of the e to the x squared plus 7. So we're essentially in this kind of case down here where we have something. Now it's semi-lagging again. So the e to the 2x, sorry, e to the x squared plus 7 came from that idea that we have to take the just thing and rewrite it again. But then our chain rule tells me that I have to take the derivative of that kind of exponent piece, if you will. So what's the derivative of x squared plus 7? Well, the derivative of x squared, the derivative is 2x. And what's the derivative of 7? The derivative of 7 is 0. So my derivative of x squared plus 7 would be 2x plus 0, or just 2x. So I just wrote the 2x piece of it. So that comes from our chain rule, where it has to tell us that we have to take the derivative of the inside. Cool. So let me erase this so people don't get confused looking at this later. And all right, any more questions about any of the chain rule ones before we move on to, I think we got to do some of the last product and quotient rule ones. I'll wait 5 seconds. All right. Why is that blinking at me? It's not a thing I need to look at, right? Yeah, okay. All right. So where are we going now? Come on, scroll. Oh, we didn't do that one? Okay, yeah. Well, like I said, we're a bit more behind than I thought we were, but that's all right. So heading back to our product and quotient rules. So here's our reminders of our rules. So I think I skipped 5 because I wanted to do it 2 ways and it was going to take too long. So with quotient rule, there's kind of this weird thing where you don't have to use it. Now, in my opinion, it doesn't make sense to never use the quotient rule. I think it just makes sense to just use it sometimes. But there are some people that literally refuse to use the quotient rule. And I'll show you how we can do that if you really want to be one of those people. So essentially, we could do this one in 2 different ways. If I wanted to do the quotient rule here, let me kind of do my little chart for our pieces again. So like I said, I kind of like doing this little chart. You don't have to do it if you can just do it in your head if you want to, but our f is our numerator, so e to the 2t, and then our g is t. We need the derivative of both of those pieces. Since it's 2t in the exponent of e, that is going to be a chain rule, or you can think about it as the e to the kt rule. Again, that is a chain rule. So essentially we have e to the 2t times 2, because 2 is the derivative of 2t, Or you think about it as bringing down that power from the e to the kt thing. What's the derivative of t? It's 1. What's t squared? It's t. So the full derivative, using our f prime g minus fg prime all over g squared, which is our derivative, our quotient rule. So f prime, I'm going to put that 2 in the front. So 2e to the 2t times t minus f times g prime. Of course, don't really have to write the times 1 because anything times 1 is itself, but I'll just write it out in full generality. All over g squared, which in this case is just t squared. If you didn't want to use quotient rule here, here's how you can do it. Now this is for absolutely any quotient rule. Again, you can use it on any quotient rule, but there are some ones that it doesn't make it any easier. But this one, it doesn't make it any harder. It doesn't necessarily make it any easier either. But anyway, what you do is you essentially take that denominator and take it to the negative first power. So here, since it's just a t, I can kind of drop those parentheses and just make it t to the negative first. If that is anything more complicated than just a t, you have to leave the parentheses, and now you have a chain rule that you're going to have to deal with. But essentially, you can. Well, I dropped my pen. Where did it go? Come back. What you can do here is once you've rewritten it in terms of the negative first exponent, it becomes a product rule instead. Whoops. So I'm going to go through this somewhat quickly, because I don't feel like many of you are gonna use this idea, but if you want to, you can. So our f prime is essentially the same, but our g prime now is a power rule. Bring the power down, subtract 1 from the power. So negative t to the negative second. That one's lagging again. There we go. That negative second looks a little gross. Negative. It didn't make it look any better. So here we would be using our product rule. So f prime times g plus f times g prime. Squeeze it in there. Note that these two don't really necessarily look the same. They are the same answer. If you algebraically manipulate one, you can totally get the other. So they are the same thing, just completely different processes. So you can technically always rewrite a quotient rule as a product rule by taking the denominator to the negative first power. Sometimes it's worth it, sometimes it's not. Like in problem 6, it wouldn't have been worth it because then you would have had a product rule inside of your quotient rule. I mean, if you really want to do that, you can, but I personally don't think it's worth the time. But anyway, if you're one of those people who really likes the product rule and doesn't like to use the quotient rule, whatever floats your boat. Questions, concerns on that one? I'll wait 5 seconds. Okay. We've got a few more of these, and then what else do we got? We've got those. We've got that one, and we've got, whew, okay. It's all right. So, oh, well, now I gotta let it catch up to me. Oh, come on, screen. There we go. So number 3, whoops, forgot to put the pen back on. Number 3, we have a product rule here. So remember, if you ever see kind of more than one occurrence of the variable, kind of in different pieces, if you will, that's going to be a product rule. So even something that, like on your homework, I know there's something where it kind of looks like this. The numbers differ by your thing, but a lot of people weren't recognizing that this is a product rule where you have ADT times e to the negative 0.4, so their derivatives were getting messed up. But anyway, maybe I should have left that up for like 5 more seconds, but it's gone now. So we have a product rule here where our first thing is our t cubed and our second thing is the natural log of t plus 1. So we need the derivatives of each piece. So we have 3t squared by a power rule. Bring the power down, subtract 1 from the power. And then the derivative of g is technically a chain rule. So we have the natural log of something. So we start with 1 over that thing. That t looks like a, let me curve that a little bit there. But then we have to take the derivative of the t plus 1. Derivative of t is 1. Derivative of 1 is 0. So this actually just does come out to be 1 over t plus 1. That's a coincidence. So now we have our 4 pieces. Just to remember, it's f prime g plus f g prime. So we have f prime times g plus f times g prime. Also, please, if I'm ever going too fast, just let me know. I still am not used to just teaching to screens. I don't like it. Yeah, I totally said it's a coincidence, and then you may not have picked up. So some people, I'm very scared to say this because people are going to remember that I say it and then did it. So I'm going to write it in red for no. Some people like to look at like the natural log of, you know, whatever 5x plus 1 and say that the derivative of this is just 1 over 5x plus 1 and then not have, you know, the other piece at the back for the chain rule. They just stop. And in this case, it almost looks like that's what's happening, but it's just because the back piece from the chain rule was just 1. So it's kind of, I realize that me just saying that looks like a coincidence wouldn't make any sense because you aren't my brain. But that's kind of what I was thinking of, is that some people think that it's just 1 over that thing and then they stop and they forget about the chain rule and that they need that second piece of the derivative of the inside. So in this case, it kind of turned out to be exactly that, which people sometimes think it is, but that was just purely coincidence because the chain rule just happened to work out like that. Anyway. Right, Savannah. We had the natural log of t plus 1. So, yeah, way back when we had an original derivative rule for the natural log of x that told us that it was 1 over x. If the thing inside that natural log is not just an x, or just a t, or just a w, whatever variable you're working with. If it's not just a single occurrence of that letter, it's a chain rule. So since it's t plus 1, it's a chain rule. If it was t squared, it'd be a chain rule. If it was 5t to the 5th plus 57, it'd be a chain rule. Essentially, anything more complicated than an x makes it a chain rule. And that works for every other thing too. We had an original, e to the x rule. If that's anything more difficult than just an x, if it's x squared, if it's x plus 1, if it's x over 2, it's a chain rule. If it's absolutely anything that's not an x, it's a chain rule. Hopefully that makes sense. Oops. I'll even say this before I go on to the next one. Savannah, and this might help you and people. Actually, if you really get into it, absolutely everything is a chain rule. So say I just had the natural log of x. Now, yes, we do have that rule that says that's going to be 1 over x, but think about this as if it were a chain rule. You would have 1 over the inside thing times the derivative of the inside thing. What's the derivative of x? It's 1. So it does come out to be 1 over x. Like, you can think about actually absolutely anything as a chain rule. It's just that if it's something that's just an x, the derivative of that inside piece is just 1. So we don't really need to consider it if we don't want to. But if thinking about absolutely everything in terms of the chain rule helps, you can do that. Or maybe that's more complicated and it scares you and you don't think about it and just consider it when it's not an x. But yeah. All right. Hopefully that was enough time before we head on to the next one. Anastasia. So Number 4, we have a product of things. We have this 3x squared plus 5x and this e to the x. So we have f 3x squared plus 5x. I'll also start trying to write slower. Seriously, just being in front of a screen, I'm like, let's just go 5 million miles an hour, and I forget that other people are trying to keep up. So we need to take the derivative of each piece. What's the derivative of 3x squared? That 3 essentially comes along for the ride, so when we bring the power of 2 down, we'll get 6x. I'm trying to like skip some of the middle steps and get us used to just jumping to the semi-simplified answer for that. What's the derivative of 5x? It's 5. We kind of have that as its kind of own separate rule, but remember that's technically a power rule. If you were to bring the power down, the power is 1, then you would get x to the 0. Anything to the 0th power is 1. G is e to the x. What's the derivative of e to the x? Since that's just an x, just our normal rule, no chain rule required. So you can use it if you really wanted to. So we get e to the x. So f prime g plus fg prime. Notice that our kind of f terms have addition, so make sure to put those in parentheses or else you'll be wrong. So f prime times g plus f times g prime. Now I know that I've said that we simplify on these, and I meant it. But because I want to, we are eventually going to have to shift to doing a little bit of simplification to help with the algebra. I want to point out one thing in this type of situation that will be helpful in chapter 4. Notice both of these have an e to the x in it. So since they both have an e to the x, I could pull it out. I could essentially factor it out. So I could have e to the x. Now I'm going to put way too many parentheses in here to just kind of keep track of everything. I could technically drop those inside parentheses, but I'm just going to keep them for a second. So I could pull an e to the x out of both of those terms. And then I could also simplify that inside a little bit. So I have a 3x squared, the 6x and the 5x would combine together to be 11x, and then plus 5. I also just personally like to write them with the highest power first. If you had left it as something like 11x plus 5 plus 3x squared, because that was kind of the order that they're written in, that's perfectly fine. So again, in terms of a quiz or exam for just finding the derivative, this line is totally fine. But in chapter 4, when we're going to want to do a little bit more with it, taking this extra step to this line down here is going to be helpful. But anyway, so we'll hold on for a couple seconds before we move on. Okay. Over to number 7. 7, now if you want to be the kind of person who does chain rule, the rewriting of the quotient rule, this would be a pretty decent one to do it on, because you would actually just come out to a chain rule instead of a product rule. But let's just do it as a quotient rule. Again, I don't really think rewriting it makes it any more or less complicated. Sometimes it can make it more complicated. So I just say just use the product quotient rule and just call it a day. But whatever floats your boat. So our f is 1 and our g is 1 plus e to the x, and I'm going to need a g squared. Let me kind of, whoops, I need to scroll up. Why the heck did that cause it to scroll? So if we want the derivative of f, what's the derivative of 1? It's a constant completely by itself. There's no x in there, so the derivative of a constant is 0. 0. What's the derivative of 1 plus e to the x? The derivative of 1 is 0. The derivative of e to the x is e to the x. So 0 plus e to the x would just give e to the x. And what's g squared? 1 plus e to the x all squared. Don't do anything else to that, just leave it. You need to do g, and it's a quotient rule. So if we scroll back up really quick to our rules, product rule doesn't have a g squared, but quotient rule does. Why does that one have a g squared and the other one doesn't? That's a trust and believe me kind of moment. Explaining why those rules are what they are is far more difficult than the scope of this class. But it's just, if it's a quotient of two things, you need the g squared. If it's a product, you don't. So here, since we had a quotient, we needed it. So the full derivative, we take our f prime times g. So I'm going to write it out as 0 times 1 plus e to the x minus f times g prime all over g squared. So we could simplify that a little bit by essentially getting rid of that first piece with the 0. Again, you could leave it, totally fine. But that type of simplification is what I would consider easy enough to just make it worth the time. Doing something like foiling out that denominator is not worth the time. Pausing for a second. Alrighty. Number 8, we also have another quotient rule. This is another one where it wouldn't be too bad to change it over to a product rule if you really wanted. But again, it's about the same amount of time either way. So let me just write these out really quick before I. So since it's a quotient, we'll need our g squared as well. So it's the derivative of e to the t. It's just e to the t because it's just a single occurrence of a variable. It's nothing more difficult than that, so we don't need a chain rule. What's the derivative of t squared? Bring the power down, subtract 1 from the power, you got 2t. What's g squared? You have t squared all squared. That one is quote unquote simple enough that you should just kind of reduce it down. I know I said you don't really need to reduce the g squareds, but that one, if it's just, you know, that one's easy enough to rewrite with our exponent rules. So just rewrite that. If you left it, I wouldn't take points off, but it's simple enough that rewriting it is kind of worth it. 1 second it takes. Use our quotient rule. F prime times g, so e to the t times t squared, minus f times g prime, so e to the t times 2t, all over g squared. There's a little bit we could do to simplify that. I don't think it's worth the time for me to explain it. We'll just kind of talk about those kind of things when we get to chapter 4. But it wouldn't even be that helpful for chapter 4 material even, but. I'll hold on a couple seconds in case there are questions, and then we will move on. This is also the last of the generic product and quotient rules, so if you have a question about like a generic product and quotient rule, let me know. Alrighty. Okay, so now we're going to move on to some of those slightly different questions. We kind of talked about some of them way back when on Thursday. That feels like 5 million years ago, but so we did do some of them, but we skipped past these tangent line questions. So let's focus on these two first. So technically, we've already found tangent lines before. We did so back in 2, 3, I want to say. maybe 2, no, I can't remember. Somewhere in chapter 2, we did an equation of a tangent line. It might have been 2-1. Oh God, I can't remember. Anyway, so back in chapter 2, so I'm going to kind of make a note that the thing I'm about to write here is in chapter 2 notes, in case you don't want to try to keep up, because I'm going to write them down really fast to just move on with our lives. We have what I'm about to write down in chapter 2. So to remind us of the process of finding a tangent line, we find the derivative. We plug the x value into f of x for our point and f prime of x for our slope. And then we use chapter 1 material to write y equals mx plus b. Again, we have that process written down already. It's just back in chapter 2 notes. I kind of mentioned back then that we were going to do it again once we hit derivative rules, and here we are. But that's a reminder of how it goes. I'll wait like 5 seconds in case someone's trying to frantically write that down. You have it. It's just not in front of your face. So we want to find the equation of the tangent line. X equals 1. That got a little dangerously close to the 1 and you can't see it. There we go. For the function x cubed plus 2x squared minus 5x plus 7. So first thing we want to do is find the derivative. And this is essentially the thing that we couldn't do fully in chapter 2. We couldn't find the actual function for the derivative, but here we can. So we're going to go ahead and do so. We're going to take, it's essentially a bunch of power rules, except the last one's a constant. So we bring the power down, subtract 1 from the power. Bring the power down, it gets multiplied by the 2 that was already there. Subtract 1 from the power. Derivative of 5x is 1. Sorry, 5. What I wrote, not what I said. Derivative of 5x is 5. Derivative of 7 is 0. So I'm just not going to tack it on the end. So now we need to essentially find two values. We need to take the value that we want. Whoops, we want the oh my lord. We want the tangent line at and plug it into the original function. So we got to plug it in 2 spots, the derivative and the original function. So we'll essentially have 3 plus 4 minus 5 when we plug 1 into the derivative. The lag is, there we go. 3 plus 4 is 7, minus 5 is 2. And if we plug 1 into the original function, we'll get 1 is 1 plus 2 minus 5 plus 7. 1 plus 2 is 3, plus 7 is 10, minus 5 is 5. So essentially what this tells us is that the slope of the line is 2, the value of the derivative. So let me get colors on this one example. I'm not going to do colors on the next one, but so 2. And then we have the point that we want to use coming from that other piece of, let me do it in blue just in case. Blue, blue, blue. So then we have a point of 1, 5. And if you remember way back when to chapter 1, when we were writing y equals mx plus b, we take that point, we plug it in, we take the slope, we plug it in, we solve for b. Subtract 2 from both sides, you get that b is 3. So y equals 2x plus 3. And that's it. So hold on a few seconds before we do the next one. So, excuse me. The next one is pretty much the same. We just kind of have a slightly more difficult derivative on our hands because it's going to be a chain rule. Same type of idea. So let me try to leave like the bottom half of that in. There we go. So the first thing we need is to find the derivative. Since that 2x plus 3 is more complicated than just an x, we have a chain rule on our hands. So we have the natural log of something, so we always start with 1 over kind of that inside something. But then we have to multiply by the derivative of the inside, which is a 2x plus 3. Oh, sorry, Sean, what?
Yeah, I just had a quick question. Like from the last round, I just caught it. Isn't for like in the middle part, like between the two squiggly lines, like isn't it oh wait, never mind. I'm sorry. I corrected my own mistake.
Okay.
Never mind. I'm sorry.
You're good. As long as you figured it out, that's good. All right. So where was I at? Middle of the chain rule. So we have 1 over that something. We have to take the something. So derivative of 2x is 2. Whoops, I forgot to put the pen back on. Is 2. Derivative of 3 is 0. So I personally wouldn't have written the plus 0, but whatever floats your boat. So I'm going to use that as 2 over 2x plus 3 before I forget to tell you that's what I did and use it in the next step. So once we have our derivative, come on computer, there we go. Once we have our derivative, then we plug in the point that we want the tangent line at, which in this case is -1. We're going to take -1 and plug it into the derivative and the original function. So if I plug it into the derivative, we'll get 2 over -2 plus 3. 2 times the -1 gives me the -2. So 2 over 1, so 2. Goodness gracious, excuse me. And then plugging it into the original function, natural log of -2 plus 3. 2 times -1 gives me the -2. Natural log of 1, which is 0. Come on, computer. There we go. So we have our slope is 2, and our point is -1, 0. There we go. I don't know if yours is lagging as much as mine, but just in case it is, I will wait for it. So once we have our point and our slope, we plug it into our y equals mx plus b and solve for b. So we've got 0 equals m is -2, x is 1, -1 plus b. Add 2 to both sides, you get 2 equals b. So you get y equals 2x plus 2. Questions, concerns on that one? We'll wait a couple seconds. Oh. Okay. All right. So that's tangent lines. Same idea. The main thing that gets more difficult is just the derivative in case your function's kind of weird. All the rest of it is the same kind of idea, just with different numbers. So, whoops. We did this one the other day, so I'm not really going to talk about it again, but remember this one's the idea of we kind of have a generic function and we need to take its derivative. So there are some like this on your homework. We're going to do some with product and quotient rule in just a second. But these ones were our chain rules. So if you're trying to do the homework and you're having trouble on the chain rule ones, kind of look back at this problem 10, maybe try to find it in the video. And just essentially remember you take the generic derivative there. I know I scrolled back up, someone asked me to, but I'm going to keep babbling about the question that I just had up there. You take the generic derivative using your generic chain rule and then use those values that you're given to plug into the correct spot. And also remember, whenever you have a composition of things, you always work inside out. Brianna, let me know when you're good. Ooh, my little camera froze. Now my little camera. No camera, come back. There we go. Okay, you're good. Cool. So let's do one of these kind of ideas, but with product and quotient rule, which is number 11. Scroll down. Come on, computer, you can do it. I believe in you. I believe in you, computer. There we go. Jeez. All right. So the first one we're asked to do is to essentially find the derivative evaluated at 2 if the original function is a product. Now, maybe I should change these in future semesters to different letters. It doesn't matter whatever letters these are. Now, this one is nice because they're F and they're G, so they kind of follow the exact layout, the exact thing that we wrote as our product. But if they were, say, S and R, like one of your homeworks, it's the same pattern. Derivative of the first times the second plus the first times the derivative of the second. But anyway, so if we were to take this derivative, product rule tells us kind of exactly what I just said. Derivative of the first times the second left alone plus the first left alone times the derivative of the second. So what we're asked to do is we're asked to just essentially, we're asked to plug in 2 everywhere we see an X. 2, 2, 2, 2. And then we've just got to replace the values into the right spots. So I need f of 2. Sorry, that says f prime of 2. F prime of 2 is 5. We need g of 2, which is 3. We need f of 2, which is 1. And we need g prime of 2, which is 6. So we have 5 times 3 plus 1 times 6. Excuse you. So 15 plus 6 is 21. So then we want to do essentially the same type of idea, but now we're given that the function is a quotient instead of a product. So again, we're kind of lucky here because they're F and G, so they kind of look exactly like, excuse me, exactly like the quotient rule. But we have the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom function all squared. Plug in a 2 everywhere you see an X. 2, 2, 2, 2, 2. Place the values in their correct spots. We have f prime of 2, g of 2, and we also have g of 2 in the denominator. Oops. F of 2, and one more. G prime of 2. Lots of colors. So we've got 5 times 3 minus 1 times 6 all over 3 squared. Whoa, lag. Oopsies. There we go. So 15 minus 6 is 9 over 3 squared, which is 9. So this reduces to just 1. Ooh, it's already 3:30. Oh boy. Questions, concerns on either of those? Hold on a second while I pull something up real quick. So then the last thing, because we're going to skip some of the last ones and we'll talk about that in a second. The last one we're going to talk about is the rest of these, which we did start the other day. So kind of to remind you what happened with this is we kind of did that same idea of the generic derivative and then plugging in 2, but here we're not given the values, we kind of have to find them. So if it's just a quote-unquote normal value, if it's f of 2 or g of 2, we wanted the y values. And then if it was f prime of 2 or g prime of 2, we had to find the slopes of, these kind of lines that we're working with here. We had to find the slopes. And that's what I have down here. We found the slopes of these lines and used them for our derivative values. One thing I'll talk about really quick, your homework. Let me jump over here really quick. I do want to apologize for this one that shows up on your homework. There's 2 that involve graphs that look like these and they're multiple choice. And I put them on there because, we talk about this type of thing and I thought it was going to be fine. And then I tried to do them myself a bit later and I realized they're a bit more difficult than I wanted them to be. So it's that same type of idea where you were using y values and slopes, but you would have to use the slope of a tangent line. So say you wanted the slope at this point right here. Why is this so thin? Slope of the point right here, you would have to find the tangent line, but then approximating the slope of a tangent line that you draw yourself is very hard. So those were multiple choice. So worst comes to worst, just guess. I'm really sorry about those ones. They're more complicated than I thought. You do have another one that I've been working with a couple of people on that looks like this. This one is much nicer. It's like the one we're just about to do, where it involves just y values and slopes of those lines. So if you're getting stuck on this one, refer to the thing we're about to do in just a second. One other thing I'll say before I hop out of here, because it's already up here right now. There is one question, I think it's like the last one or the second to last one, where you have to find the derivative of the square root of r of x evaluated at a certain point. So remember that the square root is a 1/2 power. So when you take the derivative, you would get 1/2 that function to the -1/2. But then chain rule would tell you would have to take the derivative of the inside. So you would need to be working with this. Also, nudge, nudge, wink, wink. I'm saying this loudly in case you weren't listening, but maybe I'm annoying enough so now you listen. On your homework for this one, input answer as a fraction, or else it'll get grumpy with you. So the way you want to think about it when you're trying to figure out what the fraction should be, you have 1/2 times essentially 1 over the square root of r of x, and you'll plug in a number for that r of x, times r prime of x, whatever that value is. Remember, a negative exponent is essentially equivalent to a positive exponent in the denominator. So I'll leave that up for like 5 seconds in case you want to panic, write that down for your homework. So in case no one's, words, in case people aren't keeping track of the chat, Jamie just asked, is anything like that going to be on a quiz or a test in your class? Exam, totally fair game. I actually really love these types of questions. Nudge, nudge, wink, wink. Specifically this type, the one where, well, it would be somewhat more like the ones that were in the notes as opposed to this. But these ones where you have to find like a generic derivative and then plug in values, love them a lot. If I were to give you a graph one, it would be straight lines. No, scroll up, scroll, none of this. Because again, sorry, that was much more difficult than I thought. But graphs with straight lines, totally fair game. Generic equations that you have to plug in values for, totally fair game. Love them. Computer, catch up to me, please. Because I said I was going to keep it up for 5 seconds, and now you're making me leave it up for way more than 5 seconds because you're not catching up to me, computer! You can do it! Believe in you! I don't even know if anyone else is lagging as bad as mine, but anyway. All right, 5 seconds, panic right. For your homework. All right. Otherwise, go back to the recording when it posts and find it. Back to this. I don't think we're going to get to chapter 4 today. That's very sad. Anyway, here we go. Finishing these ones. So let me clear up this kind of slope work on here so that this gets a little less busy. Now I know I didn't leave us a lot of space for these ones. Oh man, I can't zoom out a lot because I need to leave those values up there. There we go. So I am going to kind of have to smush these tiniest bit. But say I want to find h prime of 1 if h of x is f composed with g. So here I want to find a generic derivative of a composition first. So we got to use our chain rule. And I'm going to take 2 baby steps at once and just replace all of my x's with 1 at the same time. No space. But the derivative of f composed with g, derivative of the outside, so f prime, evaluated at the inside, so g of 1 in this case, times the derivative of the inside, so g prime of 1. Come on, you can do it, computer. There we go. Oh, also, well, I'll hold on a second for y'all to write that down, and then I'll do something else. So we found slopes the other day. So we found the slope of this line to be 2. So let me just write that out here. So slope of this part is 2. We found that right here. That was with, jump over 1 space, which is technically over 2. And then we went up 4. 4 divided by 2 gave us 2. Slope of this line came out to be -1. And then we kind of have this third option up here, which is a straight horizontal line, so the slope of that is going to be 0. So just in case we need any of those slopes, we now have all 3 options. So composition, always work inside out. So I need g of 1 first. So 1's approximately here. So on our function g, that would be up here. What is our y value? It's 7. So we would have f prime of 7 times g prime of 1. What's the derivative of f when we're at x equals 7? We're on that horizontal piece. So at x equals 7, we're on that horizontal piece. So the slope of that piece is 0. So f prime of 7 is 0. G prime of 1, since the slope of g is -1 everywhere, slope of g prime of 1 is -1. So 0. Explain what more? The slopes? Why the slopes are what they are? So f prime of 7, right. Where is f prime of 7 on this graph? So here's x equals 7. So let me go up to 7 on the graph. It's right here, that little red dot. That's f prime, that's f of 7, f of 7. So if I want f prime of 7, I want to know the slope of the function at that point. Since these are straight lines, the slope of the function at that point is going to be the slope of the line at that point. So since the line at that point, since at f of 7, we're on kind of this horizontal line piece, what's the slope of that horizontal line piece? That slope is 0. So that means that f prime of 7 is 0. And again, in general, on quizzes or exams, you would have these straight line pieces. And similarly then for g prime of 1, well, g prime is one singular line, so we really only have one case for slope. What is the slope of that line? We found it was -1 the other day, so I just pulled out the -1 again. All right. Any more questions on that one? I'll wait a couple seconds before we do the next one, which is essentially the very same type of idea, but now our composition is just backwards, if you will. Okay. Need a generic derivative first. Oh, why did you zoom in? Generic derivative first. So we have a chain rule again, but again, now our composition is kind of switched. So our outside function is g. Oh, and I'm going to plug in 2 again at the same time. So g prime of f of 2, derivative of the outside evaluated at the inside, times the derivative of the inside evaluated at 2. Whenever you have a composition, you have to work inside out. So we have to find the f of 2 first. What is the y value of the function f at 2? That y value is 4. So we have g prime of 4 times f prime of 2. G prime of 4, what is the slope of g at 4? It's the same as the slope of g everywhere, so -1. Times the slope of f at 2. At 2, we're kind of in this first line segment for f, since f is made up of kind of 2 line segments. What's the slope of that line segment? That line segment has slope of 2, so f prime of 2 is 2. So -2 is our final answer. For this last one, we have a quotient, so we need to use our quotient rule. So I have a bit more space here, so I'll do it the generic one first. So the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom all squared. All squared. There we go. And we want to plug in 6 everywhere. So maybe I should have still saved myself some space and just plugged in 6 right away, but oh well. Whoops. Whoosh. I'm going to run out of space again. There we go. So let me find all of my kind of generic values first, the actual y value. So we have 3 y values here. Well, technically 2. We need to find g of 6 and f of 6. So let's go ahead and find those first. So we'll have something, and then something squared, and it looks like a little face on the top. Anyway, so g of 6, where is 6? Where is g? Go over to the y value. What's the y value at x equals 6 of g? It's 2. So g of 6 should be replaced with 2. F of 6, go up to 6 on the function f. Go over to its y value. What is it? It's 8. So we should replace the f of 6 with, oh my goodness, with 8. And now we need our slopes. We need f prime of 6. At f of 6, we're on that second line piece, that horizontal line piece for f. So what's the slope at 6? The slope would be 0. Oh, I forgot to put an f of 6, g of 6 in the denominator. G of 6 in the denominator, we found g of 6 to be 2. So inside of those parentheses should have been 2. I should have put that down already, I'm sorry. And now all we're left with is to find g prime of 6. What's g prime of 6? What's the slope of g at 6? It's the same of g, it's the same as the slope of g everywhere, which is -1. So we'd have 0 plus 8 over 4, so 2. Questions, concerns about any of that? So again, we have our y values that just come from the y values of the function. So any just f of something or g of something was a y value. And then any f prime has to be a derivative value, has to be a slope. Because remember, the derivative values give you slope. Remember, derivative is a slope. Get that in your brain if it's not there already. Derivative is a slope. So since these were straight lines, we could just find the slopes of the lines in general, and then we just wanted the slope of whatever part of the line the point was on for that derivative value. All right, we have about a little less than 15 minutes left. So I'm going to pause for like 5 more seconds in case there's any questions before we jump over to getting an introduction to chapter 4. We're not going to get too far in 15 minutes, but we'll at least get a couple ideas under our belt. Alrighty then. Going to chapter 4 then. Oh man, I think there's one person in this class that like a month ago or even longer asked me to send them notes, and I sent you chapter 4 notes, and then a few days ago I decided to rewrite them. So your notes are going to look the tiniest bit different from mine if you still have those, if you printed them out when I sent them to you about a month ago. Like this thing down here is not in your notes, but the large majority of it is exactly the same. But anyway. Oh yeah, I forgot to talk about this, Savannah. There is another page on chapter 3. I'm skipping it. Here's the reason I can skip it. I'm going to put the answers up on Blackboard. So if you want to look them over, you can do so. Those last 3 questions in chapter 3 are essentially questions from chapter 2 that we were just now going to be able to use the derivative for. So we already know how to do those. And for the sake of time, because we need to get to chapter 4, I'm skipping those 3. You can look on Blackboard. I'll post the answers to them. They are exactly stuff that we did in chapter 2, or maybe even earlier sometimes. So they're old material. It's just that instead of estimating the derivative value using the f of b minus f of a all over b minus a, we could actually find it using derivative rules. But I did forget to mention that, Savannah. But we are going to move on to chapter 4. So, chapter 4. Chapter 4 is all about finding maximum and minimum values for a function. So we're going to kind of introduce that idea, and then we'll talk about it way more on Thursday. So remember, derivative tells you slope. Well, I meant it when I said that's important. Derivative tells you slope. So that can essentially provide us information about whether a function is increasing or decreasing. And then remember, the second derivative tells us about concavity. So it tells us about kind of how the function is curving. And remember, we have this relationship kind of chart, if you will, between the 3 different types of functions we have now. The original, the first derivative, and the second derivative. We wrote this down before, I believe, in section 2.2. I think that's a lie, 2.4. I think 2.4 we wrote it down originally. But we're going to write it down again because it's really that important. So what it was is that if the first derivative is positive, then the original function is increasing. If the derivative is negative, the original function is decreasing. And in that point, we can't say anything about the second derivative yet. And if the second derivative is positive, first derivative is increasing. Original is concave up. Second derivative is negative. First derivative is decreasing. Decreasing. Original is concave down. I'll give you a few seconds to write that down. So These relationships are essentially going to help us to discuss the shape of a graph without needing to have the picture of the graph in front of our face. And specifically, it's going to help us find maximum and minimum points. Again, I would just suggest committing this to memory if you can, or at least being able to kind of think it through if you need to, because the relationships between these, again, they're used so very often that you're going to want to be able to go frontwards, sideways, backwards, all sorts of things. So I'll kind of leave that second piece in case anyone hasn't caught up yet. But some definitions. So a function f, say we have a point P in the domain of a function f, then f has a local minimum at P if f of P is less than or equal to the values at P for points near P. And I'll kind of explain this points near P in a second in case that's weirding you out. And we have a local maximum if f of P is greater than or equal to the values at P for points near P. So say I had some function, it looks like this. This point, and this point would be local mins, local min, local min, local min. And then these 2 points here and here would be local maxes. Local max, local max. Catch up with me, computer. You can do it, I believe. I believe in you. There we go. So what I mean by values of P for points near P, notice that this point, kind of in the middle, if you will, is lower than the other 2 local mins. That at this point in time does not matter. It'll matter later for something else, but it doesn't matter. What we mean by local maxes or min is kind of like in a nearby neighborhood. Is it the highest or the lowest thing in that kind of neighborhood? And that's what makes it a local max or a local min. It doesn't matter if if eventually there's a point that's lower than it. Doesn't matter, as long as kind of in a neighborhood around it, it's the lowest or the highest thing. 5 minutes. I'm going to introduce the next, well, not the next thing, it's not different than this, but I'm going to do this bottom thing in the last 5 minutes. So say we look at this function right here. Say we wanted to estimate the x value. I know the x values are kind of blurry. Essentially, every little squiggle you see is a 1, so it goes up by 1 each time. So estimate the x value. You will, I'll tell you about it in just a second. Estimate the x value at which a function attains a local minimum. That's going to be this point down here. So that's going to be the minimum. At what value? So what value is that min at? That looks like x equals 1. So we look like we have a min at x is, I'm going to say approximately equal to 1. Maybe it's not exactly 1. We're not sure yet. What would the value of the derivative be there? So remember, derivative tells us slope, and specifically slopes of tangent lines. So if I take my kind of tangent line right there, that looks like the derivative at that point would probably be 0. I'm still going to write approximately, just because I'm not saying it is or it's not. It's going to be, but it looks like it's probably going to be about 0 there. And then what about to the right and to the left of it? Well, if we remember that positive means increasing, negative derivative means decreasing. To the left of this min, we have something that's decreasing. So to the left side of this point, it looks like the derivative is going to be negative because the function's decreasing. Whereas if we look at the right side of this min, we have an increasing piece. And if it is increasing, then the derivative is going to be positive. I know I'm running out of time. But really quick, and then I'll talk about your quiz. We'll go over, I'll reiterate this last piece on Thursday, but essentially what's going to happen is when we look at our max, it's kind of going to be the opposite. To the right, it's going to be positive, and to the left, it's going to be negative. When I say it, I mean the derivative. And that's not a coincidence. That's actually what we're going to be using to find whether these are maxes or mins. So essentially what we're going to be doing is chapter 4 is we're going to be using the derivative to be able to find where these maximum and minimum values are for a function. We're going to be talking about that a lot more on Thursday, and we're going to finish chapter 4 on Tuesday because I don't think we'll finish it on Thursday. Your quiz this week, so quiz on Thursday will be on derivative rules again, but it's going to focus on chain and product and quotient rules. It's going to be similar to the last one where it's just, here's a function, find its derivative. But it's going to be chain and product and quotient rules. But you won't have to do anything with them. You'll just have to find them and write their equation. You will not need to simplify them. I would actually prefer you don't simplify them, but that's how that's going to go. So 2 minutes early. I could have kind of finished that last piece, but it's okay. We'll reiterate it on Thursday because some of y'all probably checked out already, which is okay. So your homework tonight, that's the chapter 3 material. Oh, remember, that's actually a good point. So remember your Wiley homework that's due tonight is the chapter 3 material. There's a lot of, some of it's just literally find the derivative, plug in a value. And then there's others that are very similar to kind of the things we finished up chapter 3 with, the one with the graph and the one with the generic, plug in values kind of deals. So there's a lot of, these types of ideas on your homework. And then remember on Blackboard, there's some extra practice that's not official. It's not being graded. It's not being collected. But that's why your Wiley homework is shorter. Your Wiley homework is shorter because there's those practice problems up on Blackboard because Wiley can't handle those types of problems. It's horrible. But anyway, I would suggest doing at least a subset of those, as many as you need to feel confident that you can do those questions. On Blackboard, there's the answers, and there's completely worked out solutions if you scroll down a little farther. So don't just scroll down to the answers. There's also completely worked out solutions if you need those too. I thought I mentioned that in the beginning, but maybe I didn't. No, wait, I don't think I did. I mentioned it in my other class. Good point, Alexa. Yes, review for your next exam. I'm hoping to have it completed by the end of the week to post on Friday. I'm currently working on it, so you should hopefully have that by the end of the week to do for the weekend and up until Thursday. And of course, I'll be providing answers for those at some point as well. So anyway, we're done. We're out of time. If you have any more questions, feel free to stick around for a little bit. I do have a meeting in a little bit, but I can stick around for a little bit. Otherwise, have a good day. See you on Thursday. Let me stop the recording.